Thank you. So thank you for being back. So this is the third lecture of the mini course on blowups, Gale, duality, and moduli space. So in the first two lectures, we have discussed blowups of projective spaces at points in general position. And today we are going to introduce the second topic, the topic of moduli spaces. And also I will start discussing Gale duality. Okay, so let me start. So I saw that in the chat, there's someone asked for some references, maybe for the lecture tomorrow. I will prepare a list of references. Okay, so let me start by recalling where we are. So yesterday we were looking at sets of distinct points in the complex projective space Pn, and we considered the blow up of Pn at these points. And then we introduced the notion of Mori dream space. So we say that a blow up is a Mori dream space when I construct the Cox ring of X. So that is the ring formed by all global sections of all line bundles on X. This is finitely generated. And we saw this theorem by Mukai and Kastravet-Tevelev that says that such a blow-up is a Mori dream space if and only if the number of points and the dimension satisfy these numerical constraints. So this is assuming that the dimension is at least 3, then it is a Mori dream space exactly in those cases. And so, for example, if you take the blow up of Pn in 2 points, so this example we looked at in detail on Tuesday, if you take the blow up of Pn in 2 points, and you look at the cross section of the effective cone of X, then it has exactly this shape. So this is generated as a cone. This is generated by the classes of these effective divisors. So I recall you that the H is the pullback of a hyperplane section. I denoted by H sub I a strict transform of a hyperplane that passed through the point Pi. And I denoted by H12 a strict transform of a hyperplane passing through the points P1 and P2. So with this notation, this is the effective cone. It's generated by these 5 toric invariant divisors that I described there. And moreover, we saw that there is a chamber decomposition in this cone, which is this chamber decomposition there. And in particular, that the movable cone, the cone of movable divisors on X, in this case was the union of 2 of the chambers. One chamber is the Nif cone of X, the one in green, and the other chamber was the Nif cone of a small modification of X. So let me recall this example from last time. So on our variety X, we could look at the L tilde, which is the strict transform of a line passing through 2 of the points. This line or this curve can be blown up, and then the exceptional divisor could be contracted in the other direction. And in this way, we define this birational map, which is an isomorphism in codimension 1. So outside the strict transform of the line and the image of this Pn minus 2 in X prime, these varieties are isomorphic, so we can identify their cone of effective divisors. And in this way, we identify the Nif cone of X tilde with X prime with a chamber of the effective cone of X. Okay, so this was the example that we explained last time. And let me just remind you also that when the dimension is at least 3, we have already seen that the X is not funnel. We computed the intersection of the strict transform of the line through the 2 points with the anticanonical class, and we saw that this was negative. And in fact, if you locate in this picture the anticanonical class, you will see that it lies in the interior of the Nef cone of X prime. In other words, it is an ample divisor on X prime. So even though the blow up of Pn in 2 points is not funnel, after you do the flip of the strict transform of the line, then you get to a funnel variety. So this is a different point of view on this problem. So if you start by blowing up Pn at a certain number of points, as soon as that you have 2 points, you don't have a funnel, but there is still a chance that after doing some small modifications, you get to a funnel variety. So in this case here, we would have just to flip 1P1. And now let's go back to the theorem that we discussed last time. Let me recall that the blow up of Pn in M points is a Moore-Trim space if and only if we have this constraints on the number of points. So either the dimension is n and you blow up at most 7 points, or in the case where dimension is 4, you can blow up at most 8 points. And in general, for n greater or equal than 5, you can blow up n plus 3 points. And the goal for today is to describe the Moore chamber decomposition of the effective cone in this case when X is the blow up of Pn and exactly n plus 3 points. So in a sense, as we start, we blow up more and more points, the geometry becomes more and more complicated, and eventually it becomes infinite. So what we want to understand is the most complicated case before it becomes infinite. So we want to give a similar description as we did for the cone of effective divisors on Pn blown up at 2 points. We want to do the same thing for the general case when we blow up Pn in n plus 3 points. Okay. So what do I mean by to describe the birational geometry? So let me recall you that when you have a Moore-Trim space, we know that the nth cone is generated by finitely many base point free divisors. And moreover, that we can write the movable cone, that is the cone of divisors generated by the divisors without a base component. We know that there are finitely many small modifications, pseudo-isomorphic varieties to X, such that the movable cone of X is the union of the nth cone of all these small modifications. So our goal is to actually explicitly describe the nth cone and the composition of the movable cone as union of nth cones. So for the first part, actually this was known. So this was something that I stated on Tuesday. You know that the Moore cone of the cone of curves of the blow up of Pn and n plus 3 points is still generated by the classes of lines on the exceptional divisors, together with the classes of the strict transforms of the lines through 2 of the points. So by knowing this, and then dually, you can compute the cone of nth divisors on X. So this is easy. This is the same computation as we did last time. And now what I want to do today is to give a combinatorial description of the Moore chamber decomposition on the effective cone of X. So this is what we want to do today. So for instance, this is the picture that I want you to remember from the blow up at 2 points. In that case, remember we had the nth cone, and then we have a small modification that was obtained by flipping the strict transform of the line through the 2 points. And in this case here, the anti-canonical class was in a different chamber, meaning that it was the X prime was in fact an ample class on X prime. So we will have the same picture in the case of the blow up at n plus 3 points. Although here, of course, we have many more chambers, but still, after we compute this, you can check that the anti-canonical class is at least in the cases when n is even, this is in the interior of a chamber, and that will give us a funnel variety that we may hope to describe. Okay, so in this case, we will describe when n is even, the anti-canonical class again will be in a chamber, and we will give a description also of this pseudo-isomorphic between X and what we call its funnel model. Okay, just before, so we are looking at the case where n is at least 3, but let me just briefly remark that there's also something meaningful to be said in the case when the dimension is 2. So we are in P2 and we blow up n plus 3 points, in this case 5 points. So let me recall that in this case, so S is a del peso surface of degree 4. And in this case, as we have discussed in the first lecture, the effective cone of the surface is a cone generated by 16 extremal rays, which are the 16 lines on the quartic del peso surface. And in this case, also, there are many different realizations of the surface as the blow up of P2 in 5 points. So let me describe all this realization. So whenever you fix one of these 16 lines, so you take one line L, then there are 16 lines on the surface, and they have a very special incidence relation. So for instance, if whenever you fix a line, there will be exactly 5 lines that are incident to the fixed line L. And then, so you fix your blue line L, and then that gives you the 5 lines that are incident to L. And then once you have these 5 lines, then this gives you a possible realization as the blow up of P2 in 5 points. You just contract these 5 lines that are incident to L. And okay, this gives you the blow up at P2 in 5 points, and your other curve L is sent precisely to the conic passing through this 5 points. So this is a classical picture, and but you see that it's so that you see that from the effective cone you get information about the possible realizations as the blow up. Okay, and now in order to describe what happens in higher dimensions, then I have to introduce it's called the moduli space of parabolic vector bundles. So let me explain what this is. So first of all, this is going to be parabolic vector bundles on P1 with n+3 parabolic points. So we fix projective line P1, and we fix n+3 points in the line. And now I will say what a parabolic vector bundle is. A parabolic vector bundle on the pointed line is nothing but a rank 2 vector bundle on P1, together with, for each of the n+3 parabolic points, I take a linear subspace, a one-dimensional linear subspace on the fiber of the vector bundle over this point. So for every pi, I take a linear subspace of dimension 1 inside the fiber EPI. So this is what we call a parabolic vector bundle. And what we will discuss now is a moduli space for parabolic vector bundle. So in general, as the usual theory for moduli spaces, one cannot just construct a nice moduli space of parabolic vector bundles. We have to define a suitable stability condition, and then we can construct moduli spaces of parabolic vector bundles that are semi-stable with respect to this condition. So let me introduce the stability conditions for parabolic vector bundles. So in order to define the stability, I need to fix what we call weights. So, so this is just a picture how we visualize parabolic vector bundles. If I take the projectivization, so E is a vector bundle of rank 2 on P1. So if I take the projectivization of E, this is a P1 bundle over P1, and each of the parabolic directions can be seen as a point on the fiber over the corresponding parabolic point. So this is how I visualize a parabolic vector bundle. So I can think of this as the projectivization of E together with some points over the fiber, on the fibers over the points Pi. Now to define the stability condition, I will have to fix a weight. So for each weight, I will have a stability condition. So the weight set is a set of n+3 weights. So these are real numbers between 0 and 1. And once I fix a weight, I will define the notions of degree and slope of parabolic vector bundle. So the degree of a parabolic vector bundle E is just the usual degree of the vector bundle E plus the sum of the weights AI. And okay, and now I have to define the degree of subbundle of a vector bundle. So if I take a subbundle L of E, the degree with respect to A of this line bundle is going to be the usual degree of the line bundle, plus I will sum the weights, but not all the weights AIs. I will just sum the weights AIs for which the parabolic direction is contained in the line bundle. So in the case, let me just draw a picture of this. If I take a subbundle L, this will correspond to a certain section of my ruled surface PE, and I will just count the weights for which the section passes through the parabolic direction. So this would be, so this is a picture illustrating how I compute the weighted degree. And now, of course, as usual, we define the slope of a vector bundle to be the degree divided by the rank. And then we say that a parabolic vector bundle is semi-stable with respect to this weight or stable with respect to this weight if for every subbundle L of E, the slope of L is less or equal than the slope of E. And well, I said I put here semi-stable, and if I have strict inequality, then we say the vector bundle is stable. Okay, so we fix n+3 parabolic points. We fix a weight vector, and then once we fix this, we can define the moduli space of semi-stable parabolic vector bundles with respect to this weight, having degree 0 and rank 2. So these are the moduli spaces that we define once we fix a weight. And okay, so I decided not to say too much about such moduli spaces. So I think this would require possibly at least another lecture to discuss the basics of this. I decided not to say too much about parabolic vector bundles because tomorrow I will discuss vector bundles on surfaces, and then I will spend more time for that. So here for today, so I'll just give you some information about this line bundle, this vector bundle, this moduli spaces. So for instance, if I consider the open subset parametrizing mu stable vector bundles, this is always an open subset of the moduli space. And in fact, is that if this open subset is non-empty, then it is in fact smooth of dimension n. So this, so to see this, you need to learn a little bit more about the theory of moduli spaces. So let's just believe on this for this lecture. And let me give you some examples. So for instance, if I take as a weight, I take one parabolic point with weight 1, and all other parabolic points having weight 0, then it's actually easy to see that in this case, this moduli space is empty. And this is because if I take, well, I can take, well, in this case, the only vector bundle of rank 2 that I have is in this case, that you can take the vector bundle, the trivial vector bundle, O plus O. And so here, I'm giving weight 1 to one of the parabolic points. So this, so given any point in the fiber of the vector bundle, so I mark this in the picture, I can always take a trivial section passing through this point. So if I take this trivial section passing through this point, this is giving me a subline bundle of degree 0. But since it passes through the parabolic direction, when I compute the degree of this parabolic line bundle, this is going to be 1. So this line bundle destabilizes my vector bundle E. So this is any rank 2 vector bundle on P1 with this weight will have a destabilizing subsheaf. So in this case, the moduli space is empty. And there are, let me just discuss another case when I take all the weights to be 0. So in this case, the moduli space is a point. So in this case, so let me just, so this is the picture from last time. This picture still applies to this case, but now the when I take, because all the weights are 0, now I always have a semi-stable, sorry, a strictly semi-stable subsheaf L. So this with the same slope. And in this case here, so in this case, every no line bundle is stable. So the stable part is empty. And in all these points, as a moduli space, this point has only one element. So you have only one possibility for the vector bundle E, which is the trivial vector bundle, and this always is destabilized. It's destabilized by a line bundle of rank 1. Okay, so in this case, this is just one point, and what is much harder to prove, but what can be seen is if I take now as the weight set, I take epsilon, I take n plus 3 weights equal to epsilon, where epsilon is a real number that is sufficiently small. Then in this case here, we get that the moduli space is a projective space Pn. So this is harder to show, but okay, let's believe this. So in general, let me now describe the work of Bauer. So this was already done a long time ago. So this was a theorem from 1991, where Bauer studied all these moduli spaces of parabolic vector bundles on P1, and he described the weight polytope for this problem. So in other words, he looked at all the weights from between 0 and 1 for which the moduli space MA was non-empty. And he showed that this is a certain polytope inside the hypercube. And it turns out that he showed that this is what is called the demi-hypercube. So you take inside the hypercube, you look at the half of the vertices. More precisely, you look at for every subset of the index set from 1 to n plus 3. For every such subset E, we can have a vertex of the hypercube consisting of the points with coordinate 1 if the index I belongs to the set, and coordinate point 0 if this index does not belong to the set. So these are the vertices. These are the 2 to the n plus 3 vertices of the hypercube. And for the polytope delta, I only take those vertices that are even, with an even number of coordinates equal to 1. So this is the demi-hypercube. So this is a polytope that has been very much studied from combinatorics. And I put here some pictures of the demi-hypercube. Okay, so this is in the case when n equals 3. This is very easy to visualize. You just erase half of the vertices of the cube, and then in this case you get the tetrahedron. When n equals to 4, now this is harder to picture, but okay, I still try to go. So this is from Wikipedia. So I just have some, this is an illustration of what would be the demi-hypercube for n equals 4. And then you can even try to get a picture of what would be the case n equals 5. Again, this is from Wikipedia. It's a bit hard to visualize what this means, but anyway, there are ways of trying to look at this hypercube. So the important thing that I want to point out is that this is a very symmetric polytope, and this has been very much studied from people from combinatorics. And so going back to the work of Bauer, so Bauer not only described this weight polytope consisting of weights with non-empty moduli space. But he also gave a chamber decomposition, in other words. So let me just state precisely what is the chamber decomposition in this case. So this is just a bunch of hyperplanes inside the Rn plus 3. And let me describe what this is. So for every subset of the index set from 1 to n plus 3, I can consider, and for every integer between 2 and n over 2, I can take, I can consider this hyperplane. So what this is saying is the following. You have your demi-hypercube with half of the vertices of the hypercube. And what you do is basically you take for any n plus 3 set of this vertices that form, they will span a hyperplane, and it will be a hyperplane precisely of this form. So basically you take your you take half of the vertices of your hypercube, and then you take basically all the hyperplanes that are spanned by subsets of these vertices, and this is the chamber decomposition. So this is a hyperplane arrangement, and when you look at the complement of this hyperplane arrangement, you get the chamber decomposition. So this was already done by Bauer, and moreover, Bauer also described what happens when you, with the moduli space, when you cross one such hyperplane. So this is, so these are the hyperplanes. So whenever you have one hyperplane of this type for one choice of index set I and one choice of integer k, you get this hyperplane. And then he explained how the moduli space changed if you change the weight A minus to the weight A plus. And here what it does. So if the k is equal to 2, then when you cross this hyperplane, the stability condition changes in such a way that the new moduli space M with respect to the weight A plus is the blow up of the moduli space with respect to the weights A minus in one point. And moreover, when the integer k is greater than 2, then the moduli spaces change as follows. So for k at least 3, then to go from one, when the weight crosses this hyperplane, the moduli space changes as follows. So inside your moduli space A minus, you have a P k minus 2. So for k at least 3, this is going to be have dimension at least 1. And then you can, again, this is exactly when, in the case when we blew up the strict transform of a line between 2 points, this projective space can be blown up, and then this becomes the exceptional divisor, and this exceptional divisor can be contracted in the other direction, and this is this contraction here gives you the new moduli space MA plus. So as before, what you have here is a pseudo-isomorphism between the moduli space with respect to the one weight and the moduli space with respect to the other weight. So this was this work was done by Bauer. So he understood very much this moduli spaces. And then what Mukai observed later on is that in fact this gives us the Mori chamber decomposition for the moduli space of Pn blown up at n plus 3 points. So here I'm drawing a cross section of the effective cone. So here I'm writing R to the n plus 4. So this is as a vector space. This has dimension n plus 4. So this is generated by the class of a hyperplane and the class of the exceptional divisor. So this is a vector space, not the effective cone. And to describe the effective cone, what we do is we take a cross section of this effective cone. And the effective cone then can be described as the cone over the demi-hypercube described by Bauer. So the purple polytope is the demi-hypercube that I have just described. And moreover, the more chamber decomposition of the effective cone coincides with the weight chamber decomposition of the weight polytope given by Bauer. And so this is what I have just described. And so, for instance, let me recall you that when we had the PN blown up at 2 points, then in order to go from our blow up to the funnel model, we had to flip the strict transform of the line through the 2 points. So this was the first example. And now, given the Moore chamber decomposition of the blow up of Pn at n plus 3 points, we can do a similar description of the funnel model, namely, in this case, when we have n plus 3 points, you have the lines that connect these 2 points that are important curves will give you important curves on X. But there's another important curve, which is you have a unique rational normal curve passing through P1 up to Pn plus 3. And you can then, in order to describe the funnel model, this is what we do. So first of all, for every pair of points, Pi, Pj, I can flip the strict transform of the line passing through P1 and P2. Okay, so I will flip all of them. And then once I flip all the lines, I will also flip the strict transform of the rational normal curve through the n plus 3 points. Okay, so I flip all these curves, and then I will do the following. Now, for any choice of 3 points, Pi, Pj, Pk, I have a P2 spanned by these 3 points, and then again, I can flip this P2. Okay, so I flip all these P2s, and then there are some new P2s that we don't see at first, which are the following. For every choice of one of the points, I can look at the cone, the singular cone that is obtained by the join of this fixed point and the rational normal curve Cn. So this is, in general, this is going to be a singular cone, but after I blow up the n plus 3 points and I flip all the lines and the strict transform of the lines, now this joins of the point and the curve becomes isomorphic to P2, and then I blow, and again I can flip this P2. And then I keep doing the same for all the linear subspaces in order of increasing dimension. So I flip the lines, and then I flip the P2s, and then I will flip the three-dimensional linear subspaces all the way until roughly half the dimension of the variety of the Pn. And then after I do these flips, then I get to a funnel model. So this is a description when the n is even. When the n is odd, then in fact the central weight, which is the weight corresponding to the uncanonical class, is going to be in a ray. It's not on a chamber, and so we don't get the smooth funnel variety. Okay, so this is a way that we can use the Moore chamber decomposition to investigate this this family of funnel varieties of arbitrary even dimension. Okay, so now this is what I wanted to tell you about this this blow up of Pn in n plus 3 points. And now I would like to point out something that got a little bit hidden in this picture, which is the notion of Gale duality. So in this case, when we looked at n plus 3 points in Pn, I told you that this variety is isomorphic to the blow up to the moduli space of parabolic vector bundles on P1 with n+3 marked points. So in fact, there is a, I can construct the following correspondence. So given, if you give me n+3 points on the line P1, I can embed P1 inside Pn as a rational normal curve. And then I can look at the image of the points, of the marked points P1 up to Pn+3. So in this way, I get n+3 points in Pn. And conversely, if you give me any set of linearly independent n+3 points in Pn, there is a unique rational normal curve. I can have a unique rational normal curve through these n+3 points, and then I can consider this set of P1 up to Pn+3 points on this abstract P1. So in this way, what I get here is a correspondence between this set of n+3 points in P1 up to projective equivalence and the set of n+3 points in Pn up to projective equivalence. So this is what we call Gale duality. This is a manifestation of Gale duality, but in fact, this construction. So this is very well known for n+3 points in P1, but this can be generalized to a correspondence that associates for any set of, so here I have to fix two integers r and s, and then I take for any, this correspondence assigns for any set of r plus s plus 2 points in PR, a set of r plus s plus 2 points in PS, up to projective equivalence. And this is how this correspondence goes. So if you give me r plus s plus 2 points in PR, I write down, I take some projective coordinates for these points, and I write this as a matrix. So I write this as a matrix, and I can do some change of coordinates to suppose that the first r+1 points are the points with coordinates 1, 0, 0, 0, 1, 0, and so on. So I start by taking the diagonal matrix as the first r+1 vectors. And then, well, after this change of coordinates, then I will see some matrix A, s+1 cross r+1 matrix A. And then what I do is I take the transpose of A and then write down the identity matrix of size s+1. And so in this way, I construct a r+1 cross s+1 matrix. Sorry, I construct this big matrix, and again, I look at the row vectors, and this gives me the coordinates, the projective coordinates of r plus s plus 2 points in the projective space PS. And this is how this correspondence goes. So I take r plus s plus 2 points in PR, and then I construct these new points now in PS. And so this works for any value of r and s, and this is what we call the Gale correspondence. So what we saw today was that in the case when you have n+3 points in P1, the Gale duality have a geometric realization as a moduli space as follows. So the blow up of Pn at the Gale dual points Q1 up to Qn is the moduli space of parabolic vector bundles on P1 with the parabolic points P1 up to Pn. So the Gale duality has this manifestation, and what we will see tomorrow is that in the next case, when you have n plus 4 points in P2, again, we will see that the Gale duality also has a manifestation as a moduli space. So we will see that Pn blown up at n plus 4 points can be realized as a moduli space of vector bundles on the blow up of P2 at the Gale dual points. So this is going to be the topic of the lecture tomorrow. So this is it for today.